Welcome to the second part, at least for the solutions or suggestions or hints on the solutions to the questions in worksheet number 2. But before I do that, there was a question today in the class, or a request actually, to briefly go over the, some of the things about Gauss's law. What do we mean by Gauss's law and what's all that? And I think since we have only 2 questions left and they are easy questions, I thought maybe it is a good idea to do that. So what does Gauss' law says? Gauss' law, if you remember, we had the net phi, or the net flux, is defined as over a closed surface E dotted with dA as vectors is equal to Q enclosed over epsilon. Okay, so that's what Gauss' law says. Now, this is the net flux. Now, what is the significance of this? The significance of this, as I said, this gives you a way by which you can calculate the electric field in a simpler way using this portion of this formula. Right. As long as you know what Q enclosed is, and the electric field, you can calculate it, assuming it's uniform, then the only thing that you have to worry about is dA. Okay, so you have to find what N is. A as a vector is equal to C N hat A. Okay, which N hat I showed you in class how you get that. The other thing that you can get from this formula, you can also find using the net flux, you can get Q enclosed over epsilon. So if somehow, just like we saw in the first question, if somehow there is a way of you calculate the net flux, then you can get the enclosed. You can get the magnitude of the enclosed charge, and you also can get the sign of the enclosed charge. Okay. And you know what phi net is? Phi net is simply phi 1 plus phi 2 plus phi so forth. And each one of these phi's is simply E A cosine the angle theta, and theta is the angle between N hat and the electric field E. Okay, so that's what the angle theta is between. So this is basically what the formula says. As I said, the only thing that you have to worry about is finding the area or calculating or knowing what is the enclosed charge inside your Gaussian surface. Okay. Now, the challenge in Gauss' law, or what you should do, the first thing that you have to do is to construct the Gaussian surface. That's the most important thing. So, Gaussian surface. Now, as I mentioned in class, the Gaussian surface has to be chosen in such a way that it's a representation of the symmetry of the charge. So if I have a sphere, a charge in the form of a sphere in which Q is simply rho times V, V is the volume, then the Gaussian surface will be a sphere that is, encompasses or includes that, and I can find the electric field at this point here R, whether R inside where the Gaussian surface is here, or outside when the Gaussian surface is outside the sphere. If I have a rod, or a wire, or a cable, then the proper Gaussian surface, as I said in class, it's simply a cylinder of length L, and then I have to do the Gauss law. I have to apply Gauss law in 3 surfaces. This is surface 1, this is surface 2, and this is surface 3. Now, since this is a charge this way, so the electric field is this way, and N hat is this way, N hat is this way, N hat is this way, and this means that these 2 guys will give me 0 flux because N and E is perpendicular or are perpendicular, and then the only electric field that I can calculate is from here, and we did that in class. So if you have a sheet, something like this sheet, then you can also use a cylinder like this, and again you can use, in this case, the electric field will be this one and this one, the sum of these 2 guys, but the electric field along this way would be 0 because the electric field and N hat are, this is N hat, n hat, and the electric field is this way, so the angle between them is 90 degrees, and you get no contribution from the curved surface, but you get two contributions the same. They're both positive because the electric field is this way, the electric field is this way, n hat, this is n hat, and this is the electric field. Suppose this is positive, right? So this is E, and this is n hat, and this is E. So the angle between them is 0 in both cases, and they add up. And that's all you have to do. The only thing that you have to worry about when you're doing, when you're solving questions of Gauss's law, is you have to make sure you construct the proper Gaussian surface. And number two, you have to make sure that you're doing all, or you're integrating over all the surfaces, the available surfaces for you. Okay. So let's go back to the worksheet, and let's look at the question. Question number, what is it? Question number 5. Okay, what does question number 5 says? I have, as usual, prepared. So this is question number 5. Okay, so question number 5 is telling me that I have an electric field represented by, let me just draw it in blue. So this is the electric field. Okay. That's my electric field this way, uniform, and it has a magnitude of 260 newtons per coulomb. And then he told me that in the electric field, I have a block of dipoles oriented so that they are aligned along the electric field lines. Okay, that means I have a number of dipoles here, n of them, and they are aligned along the electric field. So the angle at the beginning is the same as this is D, right? So this is D, the dipole. Okay, so D, the distance, and the electric field. So D is this way, and the electric field is this way. So it's aligned again along it. If 3.8 joules are required to rotate the solid so that the dipole direction is reversed, each dipole has a dipole moment is equal to that. So what he wants you to, or what he told you that you need 3.8 joules of energy to flip this 180 degrees. That's what he wants. You have the dipole like this, and then there is several of them. There is n of them, right? There is a block of them. And all of these dipoles, in order to flip them to this direction, opposite to the field, you need 3.8 joules. And what does he want you? He wants you to, how many dipoles are there in the block? And he gave you the dipole moment for each one of them. Now, if you remember from class, we have the work done, right? We've calculated that the work done on a dipole is equal to the dipole moment multiplied by the electric field, and then multiplied by cosine theta 2 minus cosine theta 1. In this case, theta 1 is 0, and theta 2 is 180 degrees. If you do that, you have the dipole moment is given. It's 6.2 times 10 to the minus 30. And you have the electric field, which is given 260. So if you calculate that, and of course cosine 180 is minus 1, and cosine 180 minus 1 minus 1, that is minus 2. So you get the result is something like minus 3.224 times 10 to the minus 27 joules. Okay, what is this? This is the amount of energy needed to flip one. So W, if you remember, W is minus delta U. So the amount of energy, is really 224. Okay, so 224 times 10 to the minus 27 joules. This is the amount of energy needed to flip one of them. But remember, I want to know the total energy is 3.8. Right. So how do I do that? So this is the energy joules per dipole. So for every dipole, to get the number of dipoles, so the number of dipoles will be equal to the total energy needed, total E, which is 3.8, divided by the energy per, or for every dipole. Okay, so the joules will cancel with the joules, and the dipole will go up. So you divide, which is equal to 3.8 divided by this number here, and then you get the number of dipoles, and then that's it. That's the answer to this question, question number 5. Okay? All right. Last question. What does the last question say? The last question is asking you, he gave you, let me just quickly read the question or at least remind myself. Okay, a non-conducting sphere of radius, he gave you the radius of the sphere, and it has a surface, a volume charge density rho. He gave you rho equals to 450. So he gave you rho, no, that means you can calculate Q. That's what he's telling you. Rho is equal to a number which is 450 nanocoulombs. That means I can calculate Q, which is equal to what? 4/3 pi r cubed times rho. Okay, r is being the radius of the sphere, which is 6 centimeters. Remember, you have to use 0. R is equal to 0.06 meters in order to get the total charge Q. So this is the first step that you have to do. Once you do that, then if you look back at the example we did in class today, we have E in two regions. We calculated E in region 1 inside the sphere, okay, and E in region 2 outside the sphere, and this is what we got. If you I mean, you can look it up. This is E1 when we're inside the sphere, and this is E2 when we are outside the sphere. This is R less than big R, and this small r is bigger than R. So I'm here or here. Okay? Now, what does he want you to do? He wants you to calculate the electric field when R is equal to 0.2, when R is equal to 0.59, and when R is equal to 3, R3 is equal to 0.6 and 0.06. So what does that mean? That means for these two guys, I have to use this equation to calculate E. Because that's what? That's R is less than R. Remember, my R is 0.06. So this is less than that. So for these two guys, I have to use that to calculate E. And for these two guys, I have to use this one. I have to use this equation, or this expression. Now, when I do that, I encourage you to do it in a table. I encourage you to do it in a table. So for every R, you calculate E using the proper formula, using the proper expression, right? So for the first two, you use this one. Over the last two, you use this one, this expression. And then these are the values of E for every R. When R is equal to this is E. When R is equal to that. Now the last thing, he wants you to plot it. He wants you to plot, what is this? And well, he didn't ask you to plot it, but it's nice to plot that. So if you look here, then for the first ones, it's like this. It has to be linear. It has to be linear. And then, so that's the first 3 points. And then it goes like this, something like that. Okay? And this will be R equals to 2 centimeters, almost 6 centimeters, so 5.9. And this will be somewhere 6.1 is here. And then 366 somewhere is 10 centimeters here. And that's it. That's the end of the tutorial. And until we meet next time, for the tutorial number 3, okay, which will be on electrostatic energy, electrostatic potential energy, and the electric potential. Thank you very much.